Good evening, everyone. My name is Sam, and I'm a PhD researcher at the University of Bristol, and my research centers around the use of robotic manipulators for nuclear inspection type challenges.
Thanks, Sam. So I'm also a PhD student at the University of Bristol. My name is Matt, but my research is about using ground-based mobile robots for radiation detecting and radiation mapping.
So sadly, some of you may have seen our last demo, but unfortunately we have some technical issues which have led to the robot breaking. Essentially, the cable at the back snapped, and so we have a problem. That means that we're not able to show you a full demo today. I'm very sorry about that. But that's science, you know, it happens to everyone from the school science project right up to big institutions like NASA. So just the way things go sometimes. But instead, we thought we'd talk to you a little bit about the National Nuclear User Facility, what it is, what it means, and what equipment's available. So the National Nuclear User Facility is where we're stood right now. This is the Hot Robotics Department, which is at the University of Bristol, Fenswood Farm facility. So that's where we are right now. And so we have all sorts of robotic equipment, everything from robot arms to ground-based vehicles to different sensor equipment and drones and even more, which is all available for people to hire. Anybody from academia or the industry can hire out this equipment for nuclear research. So I think Matt's best placed to speak about tracked vehicles.
Great. Thanks, Sam. So what you're seeing in front of you is two pieces of equipment we've combined. You have the KUKA arm on the top, and we have the SuperDroid HD2 on the bottom. So the SuperDroid HD2 is a heavy-duty, all-terrain tracked robot, which means it's ideal for carrying large payloads like the KUKA you see on top of it. But there's several other platforms that we have for NNUF. We have two other wheeled ground-based robots. We have the Leo rovers, which are very small, lightweight, don't weigh more than about 8 kilos, which are good for going inside small areas. We also have a ClearPath Husky, which is a much more substantial wheeled robot, which can carry similar sized payloads to the SuperDroid. We also have a small quadruped robot, which you see in the background, the Unitary A1. So quadruped robots are great for radiation mapping challenges because due to their small foot size, they pick up very little radioactive dust, which makes them well suited for areas with large amounts of contaminated dust on the floor. So how do you like it to Sam?
Yeah, so I'm going to talk a little bit about robot arms. So here as part of the National Nuclear User Facility, we have two KUKA EWA LBR arms. These are great arms. They're force torque sensitive. So in every joint, there's a force torque sensor, which means it can sense things in its surroundings. This means it can be used for human-robot interaction. So it's actually human safe. Because of the highly sensitive force torque sensors, it will detect any collisions that it makes. More specifically for nuclear applications, it's possible that you could use one in a glove box setting, for example, where you've got quite tight confined space to work in, and you might want to avoid collisions or causing damage to that confined space. We were hoping to use it as a mounting on the SuperDroid as part of our combined radioactive dispersal event device, which would allow us to actually manipulate it from on top of the SuperDroid. So the SuperDroid could drive up somewhere and the robot could then sense around its surroundings to find hot particles, for example. And it can do that because it's a very lightweight robot weighing in at just 20 kilos. Otherwise, we have some Canova robots. They're very similar to this. They're a bit more lightweight, in fact, and slender enough to, in fact, to fit through current glove box ports. So alongside the robot arms, we have a range of sensing equipment. So we have a raft of radiation detectors. We have some scintillator detectors. We have the Chromex Sigma, which uses a cesium iodide, a thallium-doped cesium iodide crystal. And the way it works is when gamma radiation hits the crystal, it causes it to glow. And you can measure that glow effect to determine how much radiation's in your environment. We also have an XRF, a portable XRF, which we have mounted on the robot arm system before, and that uses X-rays to actually determine what material you're looking at. Works best in the transition metals, and it can actually, if you're looking at an aluminium pipe, it will tell you it's aluminium. That's, again, available to hire. We also have some Raman probes as well. So one thing XRF is not very good for is actually searching for plastics and very light elements, but Raman is really effective for that. Raman uses laser light to actually detect the electronic emissions, which it feeds back, and from that resonance, it determines exactly what material we're looking at. So I mentioned as well, we have some drone systems. We have, do you know the names of the drone systems?
Yeah, thank you very much. So there are a few different types of drones. The notable ones are the Mavic Pro, which is a lightweight drone, great for doing aerial surveys, because it's got a very good camera on it. We also have some different DJI drones from the M series, including the M600, which is a much heavier drone, which is great for carrying sensor payloads to perform different types of research. So I think now we should be able to show you some footage from earlier of our dress rehearsal, which should still show you parts of our demonstration. So we'll see if we can get that running for you, so you can see what we would have shown you today if you hadn't had some technical mishaps.
Yeah, so just to give you some background, I didn't mention this at the start, but obviously we've mounted the KUKA LBR arm on the SuperDroid with an attached sensor rack. And the idea was that we'd be able to sense radiation on a ground-based, on the ground using the SuperDroid robot with a scintillator detector attached. And then when we identified the hotspot, we would then use the robot arm to actually explore that space in more detail. So that's what you'll hopefully see on our live demonstration.
Great. So as you can see on my screen now, the kind of environments that you might deploy these robots in are often quite complicated. This is the Pridneprovsky chemical plant in eastern Ukraine, which is an abandoned chemical processing facility, which is very radioactive. So you can see on the floor there's all sorts of debris and metalwork and bricks and so on, which can be quite hard for most conventional robots to move across. So this is where robots like the SuperDroid HG2 really excel. Because of its tracks, it can travel over small obstacles and even travel upstairs. So you'll see on the floor here we have a few collected bits of debris that we're going to use to demonstrate how the SuperDroid with the arm on top can traverse it without any problems. So I'll hand over to Sam.
So I'm going to step aside now. And Matt is going to demonstrate the robot moving across this debris. So as you can see, without too many issues, it's able to traverse across this pile of scrap metal, which is not too dissimilar from the PCHP plant that Matt mentioned earlier. Very well. The noise it's making, you could be forgiven for So as you can see, this robot is very capable of it's unfazed by all of the waste. Okay, so that was a nice demonstration of its capability to really drive over really rough environments. So I'm going to pass over to Matt now.
Great. So what you'll see here on my screen again is, well, as we've got a really detailed view of how the robot sees the world. So we have these multicolored points represent the point clouds that the robot is building up with its LiDAR. We also have a 2D map, which allows us to see obstacles marked out in black. Now, these colored spheres here that you see represent the counts per second of the picked up by the radiation detector. And you'll see as we move the robot around the space, it populates more of the area with these colored spheres. Now, if the spheres are yellow in color, that implies there's not much radiation around. If the spheres are greener in color or bluer in color, that implies it's a higher radiation count. So you see here, we have got a peak in this corner over here, which is getting close to where we store our sources in a safe in this corner. But we have another peak just around here. So we can move over to that point and we can create a radiation map of the area in more detail using the KUKA arm that is on top of it.
Yeah, so the KUKA arm can now position itself up against the wall. So the arm itself recognizes and has been told by the super droid that it should scan to its left. So now the system begins to move the arm right over to where it's required on the wall there, where we have our radioactive source, because we identified that hotspot that Matt showed us on the visualization screen. So the arm begins by lining itself up to the wall. We'll just wait whilst the arm does that. And then it's going to start moving across the wall, collecting a radiation measurement at every point, and combining that with the positional output of the robot arm itself, from which we can generate a rather similar radiation map to the one that Matt created from moving the robot around on the floor. So you should start to see now the positions from the robot arm populate the wall, which is shown on the RVIS screen. So there you see the first one's green, because we're not pointing directly at the source yet, and we've got a relatively low radiation count. And then as we move closer to looking at the source, we start to see a population of bluer spots. Now, this is really a useful tool for using in an extreme environment or an environment where you might want to send a person in if you're unsure about whether it might be safe. Because the robot can go in, it can work out where the radioactive hotspots are located, and then it can scan over them to ascertain whether or not the space is safe for humans. You could also very easily mount other sensor systems on the arm if you're worried about, for example, asbestos being present in the room. You could integrate, therefore, something called a Raman sensor, which uses laser light to identify different materials. And that could be used to point out hazardous materials, not just radioactive materials. So the arm's just going to continue to sweep across there and build up that radiation map.
You can also see one of the key advantages of using the robot operating system, or ROS, with this visualization. So in this case, we have four different computers that are doing different elements of processing sensor data or controlling the robot, but it can all be combined into one visualization with an incredibly low latency, and it allows you to combine all of these different sensor inputs to get a detailed map of your environment, both from a physical point of view, but also from the radiation point of view, as you can see from these colored spheres here.
Thank you very much for coming along and attending, and hopefully we'll see you at the National Nuclear User Facility sometime soon. Just stood behind our super droid, affectionately known as the Super Duper Droid, because it has the arm mounted on the Super Droid system. Cool. So I had a question come in about how intuitive the controls are. And the answer to that is it varies, really. You can obviously use all of this equipment autonomously, in which case there are no controls. But you can control it with a joystick, such as an Xbox controller, or a touchpad. There's a variety of options there. So it depends really on the application is my answer to that question. Cool. So I'm very happy to answer any more questions. Don't be shy. We're really happy to answer any questions that might arise. And if you don't want to ask a question right now, you're more than welcome to get in touch with us. If you head to the National Nuclear User Facility website, just search on Google National Nuclear User Facility, and it should take you straight there, and you can find some contact details where we'd be more than happy to take any questions you may have.
Are you doing research on this sort of system at the moment? Is this part of your current research?
Yeah, so if in case you missed that, the question was, is this part of my current research? And yes, absolutely. So Matt and myself have been working on this system, and we're hoping to eventually deploy it in Chernobyl. So obviously we've got a few things to iron out, as you might have guessed from our demo, but we are hoping to send it into the facility there, under the dome, as it were, to actually identify hot particles in rooms where they're a bit uncertain about whether they might be safe for humans. Okay, so the question was, what makes this specifically ideal for an environment such as Chernobyl? And I suppose the answer, well, Matt, would you like to take this one, or should I? Or?
Thanks, Sam. So I'll budge over Sam in frame. There's a few things that make this quite useful for deployment in Chernobyl. So one of the things they'd be interested in doing with a robotic arm in Chernobyl would be to drill holes in surfaces. So the fact that this arm has got force feedback means it would be ideal for that, because it'd be able to respond to how much resistance is going from the material and make sure it didn't just snap the drill bit. Also, the fact that it's a fairly all-terrain robot is very advantageous. It can travel upstairs with its tracks, which would mean that it can travel through all sorts of obstacles that might be inside the the sarcophagus. The fact that we can also mount a huge array of radiation sensors on it and move them around on the end of the arm means you can get really detailed information about the exact sources of radiation and use that to characterize different environments.
So you mentioned there that in September the team will be taking other pieces of kit over to Chernobyl. What sort of piece of equipment might that be, and how will they be used?
Yeah, so again, sorry, I'm not on this trip, so.
Yep, so there's a few pieces of equipment we'll be taking over. So we'll be taking over a selection of drones for doing outdoor radiation mapping. But we're also planning on taking out a Boston Dynamics spot, which we'll get through the NNUF access scheme from RACE, which is which is one of the partners of the National Nuclear Facility based in Culham in Oxford. So we'll be taking out that platform paired with some sensing equipment from a team at the University of Oxford, and we'll be using that to create detailed 3D maps of the inside of various buildings around the Chernobyl site, with the goal of eventually, on the end of the trip, deploying once or twice inside the sarcophagus itself.
Yeah, so the question was on KUKAs and what they're designed for, and what their potential applications might be, particularly around nuclear waste sorting. So the answer to that is yes, as you mentioned, the KUKA arms are primarily used for the automotive industry in manufacturing. But that's the more larger industrial arms, which you see from time to time on the news. So you're probably quite familiar with those. An arm like this, a collaborative arm, represents more of a research-based arm. I mean, at the moment, there's not too many industrial applications for collaborative arms, but it's quite a very exciting time to explore what they're capable of. You've got lots of people working with human-robot interaction. I think the University of Manchester are showcasing that today, and also using the force feedback for applications such as drilling. But I think that yes, so one aspect of my research, obviously, I'm using a lot of different sensors such as XRF and Raman probes and radiation detectors on the end of robot arms, with a view to be able to sort and distinguish between different waste items ahead of their long-term disposal. Now, one of the key advantages of using a collaborative arm in doing that is actually the force feedback allows you to actually weigh objects in situ. So the nuclear industry is very conservative, and they like to know precisely the weight and the classification of a material. So anything that you could use to sense out different materials and then weigh the object is very sought after. Okay, so we've had a question come in. I think Matt's best placed to answer it. Do you want to just tell them what the question is?
Yep. So there's been some talk of deploying the system in Ukraine, which is what the question was about. So if we were deploying it in Ukraine, we'd be taking it to the Chernobyl nuclear power plant, where it could be used to explore rooms which it's difficult to get humans access to. One of the things that we'd be looking at doing if we were to do such a project would be to mount some form of drill on top of the KUKA, which would allow it to drill holes in material and take samples of them. So one of the reasons the KUKA is excellent for that is because it has force feedback, which allows it to pick up information about how the drill would be responding to whatever surface it was in contact with.
Awesome, thank you, Matt. So the question was, what is my favorite bit of kit? So I'll start by answering it, then I'll hand over to Matt. I think my favorite bit of kit is, in fact, this KUKA LBR arm. I've loved working with it throughout the course of my PhD. I think it has a huge amount of potential. I love the force feedback that you get. You can actually run it in what's called compliance mode. So you can actually move it around with your hand, and the KUKA will just follow really loosely. So if you had something heavy you needed to pick up, you could guide the robot and it would be able to fulfill that challenge. Yeah, I've spent a lot of time working with the KUKA. That would have to be my pick.
Great, thanks. I'd say my favorite robot would almost certainly be the Super Droid, as in it's very, it's very heavy duty, can handle all sorts of terrain, and it comes with a lot of sensors already built in. It's already got an IMU, a GPS, and a LiDAR, which makes the job of anyone doing any research with it much easier, because all you have to do is add your own sensors and then you're good to go. In terms of my favorite sensor that we have, it'd probably be the Hokio two-dimensional LiDARs, just because of the huge amount of data output you get from them. So they collect around 5,400 points every revolution, do 40 revolutions a second, which means that within 5 seconds, you're already up to 1 million points, allowing you to build up really detailed point clouds just from a single two-dimensional LiDAR, which can be really useful for all sorts of mapping where you can't use information from the robot about how far it's traveled.
Awesome. So that's quite a nice system for us both to build and design then. We've got all of our favorite kit combined into one right here. So the question was, where would we most like to deploy this robot arm to show off its capability for nuclear research? And I think that there's a number of places that spring to mind. I think the most obvious one, and the one we hope to one day deploy it in, is in Chernobyl. You might have seen recently an article about a room that they have there, which is, they're just not sure what's in it. It might be safe, it might not be. So the idea for us is to actually use our Super Droid system here to investigate what might be within that room. And the first step of that requires us to drill a hole through the wall just to get a sort of initial sensor reading of what might be coming through there. So hopefully we'll be able to use a drill mounted onto the KUKA, using that force feedback to ensure that the drill bit does not break, to break through that wall to do an initial assessment. If it's safe enough, it's not going to destroy the robot system, then we'll be able to roll our system through and really learn a bit more about what's in that room. Yeah, so the question was on combining off-the-shelf equipment versus building a custom design from scratch. And the answer to that is you have a lot of problems that actually arise when you combine different off-the-shelf components. It's not as easy as it might seem. So that is certainly one problem that you face. But the main advantage of it is you have a lot of different equipment which has been verified in the field in different applications. So you have that sort of strong foundation for your research. Yeah, I don't know if Matt's got anything you'd like to add.
Yep, thanks. The advantage of using stuff you can buy off the shelf is simply just the thousands of hours that have gone into it already. So obviously we're both PhD students, which means we have 3.5 years to get all of our research done. So if we were trying to do everything from scratch, you'd be spending a lot of time just doing that. So being able to buy cutting edge equipment, such as the KUKA arm and other different platforms, means we can leverage the advances made in that and use them for our own research more effectively.
So the question was on any equipment that we would like that isn't here. I suppose in an ideal world, you would want to mount as many sensors as you could possibly fit onto the end of the arm to really understand your environment to the maximum possible level. Now, we have actually a few sensors available via NNUF, which we've been able to mount on the system itself, including XRF, portable XRF system, which enables you to perform XRF characterization in the field on a robot arm. really easily. There's no need for a benchtop lab system and taking ex situ samples over to your benchtop system away from the lab. So there's that. We also have a Raman probe available, which we'd like to integrate into this system, so that we could use it for material characterization as well. So that's one thing. Although they are available to us, it's difficult to mount everything that you need on the end of the arm, just for space reasons. So I guess that's my answer. Is there anything you'd like to add, Matt? Or?
No, that covers most of it.
It's really, yeah. I suppose that there's a lot of stuff which maybe isn't invented yet, which could be useful, make our lives easier. But you know, we'll get there eventually.
As a final note, then, what would be the ultimate invention that you think would be amazing?
The ultimate invention, I would have to say, is I think my biggest hurdle has been often just the size of some detectors. Like a portable XRF is maybe yay big. It's a sizable bit of kit. I would love for a tiny version of all the sensor equipment that we have, such that it could easily fit on the end of the arm. Anything?
Great, yeah. I think the ultimate invention from the mapping point of view, which does exist, but it's very cumbersome and not very long range, would be a LiDAR that also projects images on what it's detected. So they're used a lot for different building surveying, but it'd be amazing if you could have something the size of Verdine Puck, which also collected picture data and allowed you to not only create a point cloud, but also superimpose what it looks like to create a perfect 3D model, which is something which a lot of research is going on to at the moment.
So I suppose the last thing might be, obviously if you're looking at deploying in extreme environments, awesome thing would be to be able to use some drone to actually deploy this system itself. I think, to my knowledge, that the payloads are still quite weak for drones, but maybe one day we can fly this in somewhere. Wouldn't that be awesome? Cool. So I guess that's all for questions. Thank you very much for joining us today. It's been a real pleasure working on this project. I'm very sorry about the problem we had, but thank you very much for tuning in. Good night.